Today we're going to be talking about representing exponential decay. And so this is going to first start off with using patterns we noticed to complete the tables, and we're going to kind of talk about our reasoning. So we have two different tables. Table A here gives us x values of 0, 1, 2, 3, 4, and 25, and then it gives us corresponding y values of 2.5, 10, 17.5, 25. So we have to figure out what's happening in this to go from one to the next. So to get from 2.5 to 10, we could either add 7.5 or we could multiply by 4. If we look though from 10 to 17.5, which of those two things are we doing? So we would be adding 7.5, and if we add another 7.5, so here we're going to add 7.5 each time. So if we do that to get to 4, we add 7.5 there, we're going to get 32.5, which is good. Now, we can't just add another 7.5 there because we're jumping from 4 to 25. So if we come up with what's happening in this situation, our starting value is 2.5, and when we add that same number, that common difference is 7.5, and then we're going to multiply that by our 25. Okay, that's the term number that we got going on there. So when we do those calculations, we get 190. Okay. In table B, we have those same x values of 0, 1, 2, 3, 4, and 25, but now our y values are 2.5, 10, 40, 160. Here we're noticing that those numbers are getting a lot bigger, a lot quicker. So here, to get from 2.5 to 10, we, again, could add 7.5 or multiply by 4. So we're multiplying, we're figuring out what it is. To get from 10 to 40, we quickly notice that we're going to multiply by 4. So here we're multiplying by 4. And remember that this is called your common ratio, your common factor. So to go here, we would multiply by 4 and get 640. Now we can't just multiply by 4 again because we are jumping, making that big jump. But we could have our equation. We're starting with 2.5. Our growth factor is 4, and then we're taking that to the 25th power. So that here is going to be a pretty big number that would go in that space. Okay. So this one is, if it just goes up by 7.5 each time, this is linear. And this one, since we're multiplying by 4, this would be our exponential. Okay. This one is arithmetic, and this one geometric. All right. The next piece that we're going to be dealing with here, we're going to be dealing with algae and bloom. And it says in order to control an algae bloom in a lake, scientists introduced some treatment products. Once the treatment begins, the area is covered by algae A in square yards is given by the equation A equals 240 times 1/3 to the t, where t is timed measured in weeks. So it's really important that we're paying attention to all of those different things. All right, in the equation, what does 240 tell us about the algae? So this means that the algae, so 240 means the algae covers 240 square yards initially. So at the beginning of this all, it is covering 240 square yards. The 1/3, what does that tell us? So this says that the area covered is 1/3 from the previous previous week. Okay, so here, here we're we're dividing by 3, multiplying by 1/3 is the same thing as dividing by 3. All right, so we're going to create a graph for when t is 0, 1, 2, 3, and 4. And we want to make sure that when we're graphing this, we're going to think very carefully about our scale. And you can always, we're going to create a table of values to help us with this as well. So let me look here. Here's our graph that we're going to be dealing with. Okay. So we have our equation again of y equals 240 times 1/3 to the t power. Oh, and it was a. So this was a over here. All right. So we're going to have t is our input, and that is in weeks. And our output is a in square yards. Okay. And so they wanted 0, 1, 2, 3, and 4. So at 0 weeks, when we're starting this, the algae is covering 240 square yards. If it's getting 1/3 smaller, okay, right, it's going to cover 1/3 less area. After 1 week, we would be at 80. Taking that and cutting it by 3 again, dividing by 3, is approximately 27. It's not exactly that, but we'll just, for the sake of ease here, say 27. Continuing on then, if we cut that in third again, that would be 9, and cutting it in third again would be 3. So if we're looking at making our graph here, we know that this is our time in weeks, okay? And this is going to, I'll do it this way since I'm left-handed. This would be area in square yards. Okay, and we're having to get up to 240 or starting at 240. So let's count by, I don't know, let's count by 20. So this would be 100. So every 5 blocks is 100. And you can obviously count by whatever you want, but you just need to make sure that you're careful with what you're counting by. And here we got lots of boxes. We're just going up to 4. So let's say that every 2 boxes is 1. And so what we're doing here is needing to graph these. So 0, 240. Each box is 20, remember. We have 180. 227, so we're going to have to estimate what that is. So that's 20, half of that. So we're going to go right there. 3 would be 9. So if this is 20, we got to go a little bit less than halfway. And 4 is at 3, so that's pretty close there. All right, and that's what our graph would look like for this information. Okay. And then here's our question about how many square yards will the algae cover after 2.5 weeks. Okay, so we have to explain our reasoning for this. So 2.5 weeks is going to be somewhere in between our 2 and our 3, whether you're looking here on your table or here at the graph. And so we know that each of these is 20. So we definitely know that we need to be somewhere less than 27, but greater than 9. Because at 2 weeks, it's at 27. At 3 weeks, it's at 9. And we're somewhere in the middle of that. So this is a exponential decay question, so it would look something like this and continue on. So I'm going to guess something around in that area. So let's say 18. Now, is 18 the only answer? Is that the actual correct answer? Probably not. That's my estimate. You do need to make sure that you're somewhere between 27 and 9. I would say, you know, somewhere between 15 and 20 is probably a good guess of something, considering as we're looking at this connecting, we're somewhere below that 20. Okay, so this is where it's going to be important that you're watching what you're counting by here as well. Okay. All right. Let's look at another situation here. So the last situation we're going to talk about is insulin in the body. And a patient who is diabetic receives 100 micrograms of insulin. This graph shows the amount of insulin in micrograms remaining in the bloodstream over time in minutes. So here's our insulin. and here's our time. So obviously you get yourself an insulin shot. That insulin is going to stay with you, and then eventually it's going to kind of wear off, and then you have to give yourself more, as you get lower here. Same thing, when you take pain medication, say you take Tylenol, it's going to wear off a bit once it gets into your system, and you have to re-up and take more, okay? So scientists have found that the amount of insulin in a patient's body changes exponentially. How can you check if the graph supports the scientist's claim? So it's exponentially, which means that it needs to be either multiplying by something each time or dividing by that same thing each time. So if we started at, how much did we start at? 100, we can see that there. We go from 100 to 90. We go from 100 to 90. So how much has changed? Well, I guess we don't necessarily have to figure that much out yet. It just says, how can you check? So we would say, see if the amount of insulin that decays after the first minute is the same as after the second minute, and so on. Okay, so as long as it's continually changing by the same thing, you're good to go. All right, so here's where I was going before. How much insulin broke down in the first minute? So we started with 100, we're now at 90. We have 90 out of the 100, which would simplify, let's see, to go from 100 to 90, let's change this. We would say 10 micrograms. And I guess I should specify this is the first minute. Okay, so how much insulin broke down? 10 micrograms. We went from 100 to 90. So that would be 1/9 of it. Sorry, 1/10 of it went away. Okay, we lost 10 micrograms out of the 100. For the second minute, we went from 90 to 81. So we lost 9 micrograms. But that was the second minute. And we lost 9 out of the 90, which would still be 1/10. So we're losing 1/10 of that every single time. Okay? And this was for number 3. Number 4 says, what fraction of insulin remains in the bloodstream for each minute that passes? So if we're losing 1/9, if we're losing 1/10, I keep saying that. If we keep losing 1/10, then that means that 9/10 remains. Okay, 9/10 of what was already there remains. Okay, last thing here, let's look at, part of our last thing here is we're going to keep continuing on this process. So if each time we have 9/10 that remains, we would take 100, multiply it by 9/10 to figure out what we have left. And we're going to keep going. So we take this 72.9 and we multiply it by 9/10, we would get 65.61. And if you multiply this by 9/10 again, you would get to 59.05 micrograms. So the last thing here, describe how you would find how many. Well, with this, we would take 10 minutes would be 100, what we started with, times 9/10 to the 10th power. And that's going to tell us how much it would be. For m minutes, we would take 100 times 9/10 to the m power and plug in m for whatever that is. Okay, so here, since our b value, since our growth rate is negative, is a fraction, that means that we have exponential decay for these questions. This first number is still the original starting amount for each of these things.